suppose that I have some source of power, could be something like a battery, and I'm delivering that power into a load. It could be something like a motor, for example. Or another scenario, it could be an audio amplifier driving a speaker, or many other situations that you could think of. And so in this scenario, I want to analyze, well, what conditions are going to maximize the amount of power that I'm able to deliver to the load. So if I calculate the power that's dissipated in the load, I would like to maximize that and study the circumstances under which that would be true. But it's also interesting to look at what conditions will provide an efficient delivery of power. And what I mean by efficient is kind of minimizing the losses, so that the total amount of energy in the system, that the majority of that, or as much as possible, actually reaches the load. So how can we start analyzing these situations? Well, the idea is that we're going to represent the source using its Thevenin equivalent. Represent the source using its Thevenin equivalent. And we know that every linear circuit will have a Thevenin equivalent. So this is kind of quite generic reasoning that we can follow. So the Thevenin equivalent circuit for our source would be this, as we remember from previous videos. So there'll be an ideal voltage source, and there'll be a series resistor. So if that is our representation of the source, then we should represent our load using a equivalent resistance. So remember, we could collapse that load, simplify the circuit down into a single equivalent resistance. I'm going to call this RL for load. So we have now actually fairly straightforward circuit that we can analyze. So the question that I would like to ask is, well, how much power is dissipated in this load resistor? So to analyze the power in the load resistor, I need to know the voltage across that resistor. And of course, here I have a voltage divider circuit. So I can write down that the voltage on the load is given by the voltage divider expression. So let's write that. So the voltage on the load is the Thevenin voltage of the source multiplied by the resistance of the load times the sum of the resistances. So this is our expression for the voltage, and we know that our power that is dissipated in a resistor is V squared over R. By the way, if you don't quite remember this one, this comes from taking P equals IV and substituting Ohm's law into it to eliminate the current. And if you do that, then you end up with V squared over R. So the power in the load, let's call it PL for load, will be the voltage in the load divided by the resistance of that load. And so we have the following expression. Let's just write down voltage squared will be like this. So we'll have V Thevenin R load divided by R Thevenin plus R load. All of that is squared. And we have divide by RL. We can simplify a little bit, and the RLs, you see we have squared on the top, divide through, so that will simplify. And here's what we'll be left with. V Thevenin over R Thevenin plus RL. All of that squared multiplied by just RL. So this is the power that will be dissipated in the load. And so we can analyze this. Let's imagine that our source is fixed. So everything to do with the source, we say, okay, that's just fixed, and we vary the properties of the load. So for example, I could draw a graph of the power that is dissipated in the load as a function of the resistance of that load, and we assume the source is fixed. So the properties of the source are fixed. So let's have a look at a few limiting cases. So if the resistance of the load is 0 If I substitute 0 into my expression, I can see that the power will be 0. So this plot has an intercept at the origin. What about if I take a limit that RL goes to infinity? Well, what's going to happen there? Well, if you analyze this and you know how to deal with limits like this, then you should be able to see that PL will also go to 0 in this circumstance. So the limit RL goes to infinity is that the power goes to 0. So we will have some sort of asymptote that approaches 0, kind of out here on the right-hand side. And there'll be a maximum. And so this function, if you graph it, will have a shape that comes up and then sort of down, and will kind of tend down towards 0. Excuse me, let's put that back, and I'm just trying to clean up my little extra asymptote. There we go. So the shape of the curve will look something like this. And so clearly there is a point here at the top where we actually achieve a maximum delivery of power. And so this condition here, this is the condition of maximum power transfer. So how can we discover the condition for when maximum power transfer occurs? Well, I would like to find the maximum of this expression here. So to find the maximum, here's what I would do. To find the maximum of the power in the load, what I would do is solve for, when I take the derivative, PL, with respect to the load resistance, solve that is equal to 0 for a value of RL. And there's mathematical derivation is in the textbook. The answer that you get when you do this is the following. The condition for maximum power transfer is that the resistance of the source is equal to the resistance of the load. So this is our rule for maximum power transfer. And so this is an equation that you should remember. So you achieve maximum power transfer when the equivalent resistance of the source, the Thevenin resistance of the source, is equal to the equivalent resistance of the load. If those things are equal, the power that you deliver is maximized. And this is something that you should remember. But there's another detail that we should actually talk about, and that is whether this is efficient. So there's a difference between maximizing the power and being efficient with the power. So let's actually draw this circuit again, and we're going to think a little bit about what is actually going on during this condition of maximum power transfer. So we have a resistance R for the source and load, and these are equal. So under conditions of maximum power transfer, equal power is dissipated in the source and in the load. So yes, we succeeded in maximizing the power that we deliver to our load, but we do so at the expense of burning off just as much power inside of our source. So this is not very efficient, right? Imagine that half of your power is wasted inside of the source. That's not very efficient. So what would we like for efficient power transfer? So for efficient power transfer, we would like the source resistance, which was R Thevenin in our previous drawings, source resistance R Thevenin to be much, much smaller than our load resistance. And in that case, the total power that will be dissipated in the source will be smaller, much smaller, than the power that is dissipated in the load. So efficient power transfer is what you would want if it was a battery driving a motor or a power system driving a house or something like that. Then clearly you want efficiency in that scenario. But maximum power transfer, where we're trying to deliver as much as possible, this is something that you would want, for example, in audio systems. So you might see, say a speaker system that is specified as, say, 8 ohm impedance or 8 ohm resistance for a particular speaker. That means that the output impedance of the audio amplifier should be 8 ohms, that they should match according to this condition of maximum power transfer. And in that scenario, what we're trying to do here is drive that speaker to its full potential, as opposed to trying to be as absolutely efficient as possible. So there's different scenarios in which we would like each of these two conditions. So the thing that you need to remember is the equation for maximum power transfer, that's this one here, that the source resistance is equal to the load resistance, but you also need to recognize that is not a very efficient situation because you're actually kind of wasting half of your power inside of the source. And if you want to analyze how much power is actually being dissipated, well, the easiest way is kind of this sort of reasoning here. Where you use, say, a voltage divider and then your power equation and write it down. There are some equations that you can go directly to. Have a look in the textbook if you want those. Personally, I don't remember them. I would just work it out each time using a voltage divider, just like here. The one that you definitely need to remember is just the condition for maximum power transfer right here.